Hello everyone. Today we will go over an experiment of heat convection. And this experiment is really focused on heat exchangers and the use of heat exchangers that are related to airflow. We're really focused here also on the characteristic performance of a heat exchanger. How we can say this heat exchanger is better than another, and we also investigate what we mean by free convection and forced convection and so on. This video meant to be part of, or like a comprehensive video just to discuss the idea of how you conduct the experiment. But you have another video or a stream that you will discuss with the instructor that will go over all the objectives and all the data analysis that you need to do in that case. So there is no equations here. It's meant to go overview how to conduct the experiment in this situation. The setup, you can see it's right here on the right-hand side. This is a duct that is meant to have a control environment where the flow of the air goes from the bottom and going all the way up in that direction. So here it goes from the bottom here and goes up through the heat exchanger that is embedded in the system or kind of installed in the back of the system, and you go from the top. There is a fan inside, and the fan actually located on the top of the duct to create a kind of a laminar flow. You also have a honeycomb structure in the bottom, very similar to a wind tunnel configuration. The one you see right now is a flow meter to measure the flow speed of the air. And you also have a thermocouple before the heat exchanger that is marked by temperature 1. Another thermocouple at the end of the duct, which is meant to be after the heat exchanger, which is marked by T2. We put the heat exchanger on the back. The one that we have inside right now is a pipe bundle based. It's one type of heat exchangers. We also have two others. Not really, the first one is not heat exchanger, it's just a flat plate without any heat exchanger to do a comparison. And the third one is the fins-based heat exchangers. So we have here, what we need to do is to heat up the back side of the heat exchanger to create a heating surface. And this will be very much similar to this case. But the other two situations, we actually built a heat exchanger on the top of this flat plate. So think about it as a heater of an iron, similar to it. And we're trying to cool down this flat surface. In heat convection course or heat transfer course, you cover heat convection over a flat plate, and we have the analytical solution for it. So that makes it easier for us not to rely on any experiments. We can actually do the whole thing without having any experiments. But the flow becomes very complicated when you change the configuration in a way that you don't have an answer anymore, and you need to conduct some level of experiments to understand the performance of this type of heat exchanger. The scale of the exchanger can be very large or it's very small, from small electronics all the way to big machines. So that's part of the dimensional analysis that you study in fluid mechanics that needs to be done to take the data that you have on the scale you see right here and apply it on a smaller or larger scale compared to this one. So right now we want to see two things. We can run this case based on a free convection, and free convection means we're not really pushing air through the heat exchanger. We're just having the fan off, and the only reason for the heat or for the air to move is due to buoyancy. As the hot air gets lighter by density, then it moves upward and it's replaced by colder air, and that's what we refer to as a free convection or natural convection. And that happens in that situation here as we have it. So we set up the power at a certain value. You have to have a higher temperature to get heat transfer. So we turn this on and we set the power to a certain value. As you can see here, it's marked by power. You can see Right now it's at 59 watt, okay? Continuously, we're measuring the temperature before the heat unit or the heat exchanger unit, temperature 1, and after the heat unit or the heat exchanger unit. So this is the one on the left side, and on the right side, you have another one behind here that's meant to measure the flow speed in meter per second, okay? Currently, you have very small value of flow speed because this is convection or natural convection case, but you have to have some kind of a flow speed, otherwise you'll have no heat transfer at all. So it happens automatically as you start to see the air gets hotter around the unit itself. So in that case, this is what you need to do to operate the machine. You have to wait until it gets to steady state. You monitor the temperature to be able to eventually get to a steady state, and then you can use the equations that are meant for a steady state. You will have all the equations explained on the lecture part of this experiment, but we still have one major measurement that is needed for this experiment to be conducted, which is the thermocouple measurement. So I can show you here, that's a thermocouple that is actually handheld, okay, connected to this red screen that you see in front of you here. So this is measured the surface temperature when you have a direct contact with it. So you can see now if I contact this to this surface, it's going to measure the surface that we have here, which clearly it's a smaller value because it's very close almost to the ambient temperature. If I go inside the machine here and start to use the thermocouple, one way to access this is through the side walls. And you can see here I have a direct access to the middle part. I'm trying to get the average value of the surface temperature. So I'm trying to get to the base as much as possible. So if I have good contact, and students are required to kind of, when you get to steady state, to kind of align it and give it a little bit of a push. It has a spring there to make sure you have a good contact with the surface. Okay, if you wait enough time, you're gonna start to measure the surface temperature. If you can see now, the value increased to 26 by just holding this around 5 to 10 seconds. So the data needs to be collected here are temperature before and after the heat unit or the heat exchanger unit. Okay. Surface temperature, that is by direct contact, and students need to place this in the right place. And power, where you set it up, you need it to know how much actually heat going into the system. That's electrical power. And the flow rate. The second set of the experiment that is done for each case is to turn the fan on, which is actually can be accessed by this button here. You can see it says here fan, and you have a dial here where you can actually increase or decrease the speed of the fan. So if I go all the way to the right, you end up with the highest velocity that you could end up with. There is no one value. It depends on what kind of heat exchanger you have there, because if you have more obstructions in the direction of the flow, you will have a slower flow. But you can start to read now, we have around 3 meters per second. That's actually the maximum value you can get for this experiment. The forced convection, which is the case we're looking at right now, it's obviously give you a lot better heat transfer process compared to the free convection. Okay. So the second part of the experiment, when you actually take the heat bundle out and repeat this experiment for free convection and a forced convection cases as well. The third type is for the flat plate, and it's connected the same way. You connect the heater on the back side, like all the other cases. You can see here, you can plug in from the back side, which happens to be in the top of the one that we're already connecting right now, to get all the heating to start. It takes around 15, not less than 10 minutes to get to a steady state, and it's actually takes some monitoring to see this. Sometimes we have some tricks to kind of decrease the period where it can reach to steady state, but it takes some patience to get to this steady state too. So the data needs to be collected one more time. Here are two temperatures: surface temperature, which is the one with the thermocouple on the right side here. We have electrical power that you set up. Now it's at 60. You want to keep monitoring these values because sometimes the controller doesn't set to a very specific value. You want to get the right average, as well as the fan speed, which is measured by the flow speed inside the duct. The company also provided software where you can monitor the information that you have there, so you can actually see the direct measurements of the temperatures, power on the right hand side here, the 61 watt. Flow rate, it's already measured, but actually can easily be measured by knowing the velocity. So you do these measurements yourself. And you have T1 and T2. What is really more important screen to see here is the one that has to do with the charts. And the good thing about the charts, you can start to see when you get to a steady state. So at the beginning of this experiment, you're not going to see that kind of a steady lines anymore. These lines start to snap up and down, and I can show you this with the thermocouple. If I touch it as my body hotter than the ambient, you're going to see a sudden increase of the red line. The red line actually shows the thermocouple, which is given here as T3. So you start to see now the value of the temperature of the thermocouple is increasing as I'm touching this directly by my finger. So it has a good value. You can even set it up at different values here. So you can see the scale that you can operate with here is, let's say, 500 seconds. So it completely changed the scale. You can see now, even at the time we started this experiment, about 4 or 5 minutes ago, when we set up the power, you see a sudden increase in all of them. I left the thermocouple, and you see right now that the red color, the graph, which shows the thermocouple or the surface thermocouple measurements going back down to original values, even lower than the surface of the heat exchanger itself. So we run 3 experiments, one with the pipe bundle. We move to second case with the fins, and then with the flat plate. And we'll explain more how to apply the equations, what are the exact objectives, and what are you need to discuss in this experiment. What are the objectives of the experiment? Okay, with this, you can further discuss this experiment with your instructor. Thank you.